Arithmetic sequences are a particular type of sequence, and they are very closely aligned with linear functions. And we're going to see that today. So whenever you're dealing with arithmetic sequences, think linear function if you get in trouble. So these are examples of arithmetic sequences: 1, 4, 7, 10, 13. And if you notice, if you were saying in your mind, hey, she's just adding 3 every time, that is called the common difference between terms. And that will always be true if you have an arithmetic sequence. There will be something common that is being added between terms. We use the letter D for that. In this case, D is 3. My next arithmetic sequence: 5, 1, -3, -7, etc. Again, you might notice a common difference. This time I'm adding -4, 1, 2.5, 4, 5.5. Again, I have a common difference. I am adding 1.5 every time. Okay, that's how we recognize an arithmetic sequence. There is a common difference between terms. Okay, so let's graph these and see what happens. So the first one, the first term was 1. The second term was 4. The third term was 7. The fourth term was 13. 6, 8, 10. No, wait. The fourth term was 10. Pardon me. 2, 4, 6, 8, 10. And the fifth term was 13. Now with a sequence is discrete, so I'm not going to connect those points, but in your mind's eye, you may be seeing a line going through them. And the thing to note is that the slope of that line, up 3 over 1, up 3 over 1, up 3 over 1, that the slope, if you will, if I could draw the line, would be 3. It was also true that we established that the common difference was 3. The second sequence we had, the first term was 5. The second term was 1. The third term was -3. And the fourth term was -7. Again, we don't connect them because the sequence is discrete, but if we did, it would be linear with a slope of -4, which is also our common difference. The third sequence, the first term was 1. The second term was 2.5. The third term was 3. Pardon me, 4. The fourth term was 5.5. And the fifth term was 7. Again, we get that nice linear feel with a slope of up 1.5 over 1, or if you want to think about it in smaller increments, up 1, 2, 3 over 2. So the look of an arithmetic sequence is linear. Okay, so there is a very strong connection between arithmetic and linear. Arithmetic sequences look linear. They're just not connected. So how would we write the functional definition, the a sub n definition for each of these? Well, think about how you would write a linear equation, right? Y equals mx plus b, yeah? Y equals mx plus b. We're going to use that same sort of notion. We decided that the slope was highly related to our common difference. So a sub n, right, is equal to 3n in this case. And then our y-intercept. Well, none of these had a y-intercept because we started with the first term. But we could think about what would the first term have been. Well, this one, let's see, if I'm going up 3 and over 1, I would go down 3 and back 1. So I would have been at negative 2. Okay, this one, a sub n is equal to my common difference, negative 4n. And let's see, we're going down 4 and over 1. So if I go up 4 and back 1, looks like I would be at 9. Also, I can think about that in this way. If there were a mysterious term here in this sort of spot before the first term, what would it have to be? Well, if I'm adding 3 to go forward, I would subtract 3. Again, here, if I'm subtracting 4 to go forward, I would add 4. Okay, here we have a sub n is equal to 1.5 n plus, let's see, if I'm adding 1.5 to go forward, I would subtract 1.5 and have negative 1/2. And if I look at my picture, if I go up 1.5 over 1, if I go down 1.5 and back 1, I would definitely be at negative 1/2. So what we say is the formula for an arithmetic sequence, a sub n is equal to dn plus, and I like to call it the a sub 0 term, the term that came before the first one. So it looks a lot like linear equation. So let's find a formula. A sub n is equal to, well, first let's establish that it's arithmetic. So I'm adding 3.2, adding 3.2. So my common difference is 3.2. So 3.2n plus, let's see, if I subtract 3.2, I get 9.1. 9.2, pardon me. Wow, I'm losing my mind here. Okay, I'm adding 7, adding 7, adding 7. So my common difference is 7. So a sub n is equal to 7n. If I'm adding 7, I subtract 7, minus 5. Okay, what if someone tells me that the first term is 5 and the common difference is 2/3? Oops. A sub n is equal to 2/3 n plus, well, if I'm adding 2/3, if I subtract 2/3, I get 4 and 1/3. What if someone told me the first term is 9 and the fifth term is 21? You may want to pause the video and see what you would do with that. I'm going to go forward and say, well, if it's a lot like linear equations, then this is like the 0.19, the first term is 9, and this is like the 0.521. So if I treated it like a line, the slope would be 21 minus 9 over 5 minus 1. So that would be 4 and 12, so 3, which means the common difference is 3. A sub n is equal to 3n. And if I'm adding 3 to go forward, I would subtract 3 from the first term. Oh, plus 6. Here we go. They tell me that the sixth term is negative 2 and the 15th term is 1. Okay, again, I'm going to use that sense of I'm lost as a sequence, but I am definitely not lost if it's a line. So the slope would be 1 plus 2 over 15 minus 6, which would be 3 over 9, which would be 1/3. So that's the common difference. A sub n is equal to 1/3 n. But I don't have my first term. I have my sixth term. So how would I find my a sub 0 term? Well, I'm going to stick with this like line. If this were line, I would say y equals 1/3 x plus b. Choose one of the points. Let's say this one. 1 equals 1/3 times 15 plus b. So 1 equals 5 plus b. So b must be -4. There. So again, stick with a sense of linear if the problem is arithmetic.